right, today we did a sample problem just to wrap up our rules of graphing that we talked about yesterday. So this is the problem from the AP Bio pretest, and I asked everybody to complete it ahead of time so that we could go over it together and sort of score it and see how you would have done if this was a real AP question. So I sort of came up with some points that you would earn, and then you could sort of score yourself and see if you would have earned all your points. So the first thing that you would want to have, here's your data, and there was an explanation that went with it, that this was a lake, and there were plants growing in the lake, and it was a sunny day, and they measured the amount of oxygen production every hour given this time period. I forgot to put a title on my table, but you should always put a title on your graph. So the first point that I would want to give to you would be for remembering to put a title on your graph. I should have had a title on the table, and for the AP exam, they will typically have a title on the table. So that'll make it really easy. You'll just transfer whatever the title of the table is, make that the title of your graph, and you're all set. So I'm just going to put O2 production on lake. I just made up something, so we have a title there. The second thing that I would look for is that you correctly chose to put the right variable on the right axis. So my second point would be for the variables being on the correct axis, and you'll notice that it should be the hour on the x-axis and the oxygen on the y-axis. And remember the reasoning behind this, that this is your independent variable. This is what was changing, the time of the day. And then what was actually being measured was the amount of oxygen produced. So this was your data or your dependent variable, and that's always going to become your y-axis. On a table, typically, your x-axis is always going to be the left column, and your y-axis is always going to be the right column, so that's a good rule of thumb. So just make sure you're doing it correctly. All right, next thing is your labels. Did you label your variables, including the units? So remember, sorry about that. So remember that if you were to, for example, leave off here on this one, milligrams per liter, they would treat it as if you did not remember to label your axes. They don't have a unit for hour, so just hour, just like what they have, is absolutely fine. So labels with units. So far you could have earned 3 points, 1 point for your title, 1 point for putting the correct variable on the correct axis, and 1 point for properly including units with your labels. The next point you would get would be for making a line graph. Now, they actually told you for this one, and this was an old AP question, they actually said make a line graph of this data. But remember, our rule of thumb, if they didn't tell you what kind of graph to make, is if both your independent and dependent variable are numerical, which they are here, then you're going to want to make a line graph. I could see where somebody might get a little confused because, once you get past 12 noon, it sort of goes back to 1 again. So you might say, well, that's kind of weird numerical data. Is that really numerical data? And maybe that's why that particular year they told you to make a line graph. But for purposes of the AP exam, they should make it pretty clear. And numerical data, that's chronological data as well, should typically be a line graph. You're looking at a trend over time. So that would be another point that you would get. The next point that you would get would be for creating a proper scale on your axes. So you would want to notice here that you're going to want to start at 6 a.m. and you're going to want to get all the way to midnight. So 8, 10, I'm not going to spend the time writing out AM and PM, although the appropriate thing would be to do that. So 6, 8, 10, and there's your midnight right here. So you should have a scale that it goes from 6 a.m. to midnight. It would be okay, absolutely okay, if you started 6 a.m. here at the origin. That is okay too. But I went ahead and started it a little out from the origin. And now our y-axis, if I notice my numbers, my highest number is 7.5. So I want to come up with a scale that will fit from 0 to 7.5. So I'm going to just go to 8. So 1, 2, 3, 4, 5, 6, 7, 8. So 8, 7, 6, 5, 4, 3, 2, 1. And I'll just add in my little 0.5s here just for graphing purposes. On the real AP exam, remember, you won't have notability. You'll have to do this by hand. But they will provide you, anytime they ask you to make a graph, with a grid. They will actually give you like a gridded background to make your graph. So you won't have to worry about trying to make your lines perfectly spaced apart because you'll have that grid to help you create a scale. So keep that in mind that you will have that at your disposal on the real AP exam. All right, and then our final point would be for properly graphing the data. This should be not going past the start and the end point. In other words, your data, remember, should not start prior to 6 a.m. and it should not go past midnight. So let me add that in, and then we will continue. All right, so I've added in my line. Now, do you have to connect the dots? No, you do not have to. I would recommend it, just so you can clearly see what the trend is here. So notice that my data does not go past midnight, and it does not start before 6 a.m. Again, if you would put 6 a.m. all the way over here at the y-intercept, then that wouldn't be an issue. You wouldn't have a gap. But there is nothing wrong with having that gap there. It may look funny to you, but that is the appropriate way to do it. And you may recall that I mentioned what would be okay is if you wanted to, is you could make a dotted line. If you do that, that literally means that that's a prediction. So that would be okay. You could do that, but don't have your solid line go past your original data points. It doesn't matter how many data points you have in the middle. You can always connect the middle. You just can't go past the earliest point and the last point. All right? So that's it. That's the scoring of the graph. Now, there was one more part to the question, and on the real AP exam, it also asked this question. They wanted a prediction if the day had been overcast. I did not expect you to necessarily know where to put that prediction line. I just wanted you to make a prediction. But if you are scoring yourself and you want to know would you've gotten it right for the real AP exam, what they were going for here is, obviously by the end of the year you would know this, plants are going to be conducting photosynthesis, and on a sunny day they would do a lot of photosynthesis. In fact, that's probably why this goes up in the middle, because that's the brightest time of the day. And then as the sun goes down, they're going to do less and less photosynthesis, and that's why the line is going back down. So if you were going to make a prediction of what would happen if it was a cloudy day and there was less sun, then the real prediction line, if you want to know what would happen on the real AP exam, should have been below the original line. So they gave credit if your prediction line, even if it was allowed to touch the ends of the original line, like it could look like this, or you could have made it like this, just a really flat line. As long as your line did not go above the original, then they gave you credit for the prediction. Remember, if you make it a dotted line, that automatically means prediction. But if you wanted to make it absolutely clear, you could also do this, make a little key, and write prediction. And then they would know that the dotted line was your predicted one for the overcast day. So that's the little last little portion there. All right, last slide. Moving past this, I have a couple of examples here of just some of the things we talked about. So this graph is just to show you that, notice how you don't have to start at 0. They're showing a little break there, because if you tried to start this graph at 0, you would have ended up with something like this, and you would have had all this empty space down here, which is really a waste of space. Plus, you probably would have ended up crunching this into a tiny amount of space. So if you can't start at 0, just make some kind of a little squiggle, and you can start at whatever is logical. This is just showing what a line of best fit looks like. Again, in this class, I don't expect you to have to make one, but if you see one, it's usually done when data is very scattered. But there's a trend here, but notice that they didn't even necessarily gather data at specific points. There's sort of data, it's like a scatter plot, sort of scattered everywhere. And a computer usually does this for real scientists. They're not sitting at a table making graphs. And this last one is just to show you that not every graph ends up being a straight line. You can have graphs that curve upward, that curve up and then come back down. You can have graphs that curve up and then level off. It really just depends what kind of data you're graphing. So don't assume that if you don't have a straight line, something must be wrong. There could be a trend that's not a linear trend. It could be an exponential trend or a logistic trend or a bell curve, something like that. Or maybe there's no trend at all. All right, last thing, data analysis and conclusion. So typically you'll write a little statement about your graph. What does your graph show? For the sample one we did, you might say something like, according to this graph, oxygen production is highest between the hours of, 2 p.m. and 6 p.m. or whatever those hours were. Or you might say there appears to be a correlation between the times of day when there's the most sunlight and the amount of oxygen produced, something that describes your graph. And at the very end, you support or reject your hypothesis. We didn't have one for that experiment, but in a real experiment, you would support my data supports my hypothesis, or my data, according to my data, I would reject this hypothesis, and then you revise. Remember, you don't say that I proved my hypothesis correct. We don't use that terminology because proving it means that your hypothesis is a fact. And in science, nothing becomes a fact. It becomes a theory because we could always have new evidence later or a revised experiment that might cause us to want to modify our hypothesis. So we would say that our hypothesis is either supported or rejected. All right, so next time we're going to talk about statistics. We're going to talk about numerically how can we decide if your hypothesis is supported, especially if your data is not really obvious. Like one side of the room scores better on a test than the other side. How much better do they have to do to say that it really worked? If you're trying to get a new drug pass and especially if the drug has side effects, does the drug make people get over the sickness? Is it enough of a benefit that it outweighs maybe the drawbacks of using the drug? How do you make that cutoff? And so we're going to talk next week about the math, the statistics where you can really draw a line and say, yes, this definitely is supported, or no, this data does, we reject the hypothesis because this data is not enough of an improvement to say that we support it.